Swayam Prabha. Digital India. Educated India.
Welcome to this lecture 29 of groundwater hydrology. The topics to be covered in this lecture are subsurface, investigations of groundwater, so this is continued, and within this, so we are geophysical methods, and under this geophysical methods the resistivity method, then followed by spontaneous potential method, followed by radiation method. So, these are all the methods of logging, and under the radiation method, this natural gamma logging, then gamma logging, then neutron logging. So, these are the topics which we will be covering in today's lecture, and so we will continue with this geophysical method which we were discussing in the previous lecture. So, here that is the geophysical log, geophysical log in a consolidated rock. Consolidated rock or formation. So, in the previous lecture we discussed the geophysical logging in an unconsolidated rock or formation, and in this lecture we will consider the geophysical logging in a consolidated rock or formation, and here we have a consolidated rock or formation with various various formations at different depths. let us say number these formations as 1, 2, 3, 4, then maybe say 5, 6, then 7, 4, 1, maybe 2. And so, here this 1 represents clay or clay stone. Number 2, formation number 2 represents say marly limestone. Formation number 3, let us say it represents limestone. Formation number 4, rock formation, consolidated rock formation number 4 represent marlstone. Consolidated rock formation, rock or formation number 5 represents sandstone. The consolidated rock or formation number 6 represents sandstone. With salt water. With say let us say this is a higher density or say dense sandstone, and 7 let us say this is sandstone with salt water. So, let us say these are the rock, the 7 formations in the consolidated rock, and let us say the spontaneous potential is indicated in this green color. So, this is the spontaneous potential and here this is positive on the left side and negative on the positive on the right side and negative on the left side, and in this consolidated this one. So, it could is the clay will have a very small positive this one or almost 0. Then it is followed by, so this marly limestone will be slightly higher, then followed by limestone, it will be even higher, then followed by again marlstone. So, that will also have almost negligible spontaneous potential. Then the fifth one is sandstone. So, the sandstone will have some spontaneous potential. Then the sixth one is dense sandstone, it will even have a higher spontaneous potential, and the seventh one is this one with salt water. So, it will have a negative spontaneous potential, then followed by 4, that is marlstone, which is negligible spontaneous potential, then followed by there is a claystone, which also has negligible potential. Then lastly, it is sandstone, but with salt water. So, again, so that also has a slightly negative, but negligible. This is the second one is the marly limestone, it will have a slightly this one. So, this is the variation, this is the geophysical logging in terms of the spontaneous potential, and similarly the geophysical logging in terms of the resistivity. So, this is so here this in this case this is the increasing direction of so this is increasing direction, and the resistivity for the this one, that is clay or limestone, is quite less. Then for marly limestone it is higher. Then it is the limestone, it is even higher. Then the marlstone, it is less. Then the fifth one is sandstone. So the sandstone is higher resistivity, and the sixth one is dense sandstone, it will have slightly lower resistivity, and seventh one is sandstone with salt water, and that will have much less resistivity. Then the fourth one is marlstone, that will have slightly more resistivity than sandstone with salt water. Then again this is clay stone with low resistivity. Then again this is a marlstone. So like this. So this is the resistivity log, and then the third one, let us say, and the same thing if we represent the gamma ray. So in this case, and again this gamma ray, so it is the, this is the increasing direction. So in the first, that is clay stone, it has some gamma ray potential. Then for the marly limestone, the gamma ray potential is less. Then this limestone, it is even less. Then this marlstone, it is slightly more. Then this the fifth one is, this is the sandstone, so it is less. Then the sixth one is also less. Then the seventh one, so this is a seventh one is it's even less, slightly less. Then 4, it will be slightly is 1, and again, so this 1 and then 2. So this is the gamma ray logging. So this is a geophysical logging in a consolidated rock or foundation. So now we will specifically go to the resistivity method of logging. And in this, so basically, so here this potential current and potential electrodes are lowered in an uncased well, and to measure electrical resistivity, of surrounding media, and thereby to obtain their variation, variation with respect to depth. And here, so the multi electrode method is the most commonly used method is the multi electrode method, and in this, so there are basically short normal, long normal, and so within this, the short normal, that is electrode arrangement, then the long normal electrode arrangement, and then the lateral. So, these are the electrode arrangement. So, let us briefly discuss the short normal electrode arrangement. So, in which, so this is the short normal electrode arrangement. So, in this, so this is an uncased well, and here one side is so this is the voltmeter, and here, so this is the point M, and so this is the reference point, and so this is the A, and the distance between A and M, the vertical distance between A and M is very small. So, and of course, so this is taken from the source, that is Keyes and McCrary, in 1971, and they have, for the short normal, so they adopted a distance of AM, which is symmetrical with respect to this reference point, as a 0.4 meter. So, that is M is 0.2 meter above this reference this midpoint, and A is 0.2 meter below this one, and from A, the other electrode is the current electrode is going, and here, so it is the current, that is the ammeter, and there is an AC generator. So, this is a AC generator, and from the AC generator, so there is another current electrode which is going point B, and the distance between, the vertical distance between B and M is around 15 meters. And so, this is the short normal electrode arrangement, and now we will go on to the another the second type of arrangement for this resistivity method of logging, that is the long normal electrode arrangement. So, in this this is the uncased well, this is the ground level, and here the reference point. So, this is the reference point, and this the electrode A, which is a current electrode, and in this case the earthing is with the current electrode. In the earlier case, the earthing was with the potential electrode, and in this case the earthing is with the current electrode. And so, here there is an AC generator. So, this is the AC generator, and from the AC generator there is an arrangement to measure current, and there is this grounding. This is the point B, and here this the potential electrode. So, that is this is N, and so here there is an arrangement to measure the voltage, and this one. So, then the other electrode, that is on the top side of this reference line. So, this is the this is the reference point, and so this is M, and the distance, this is or M dash. So, this distance adopted is about this AM dash is 1.6 meters, which is symmetrical with respect to this reference point. And again this M dash N, this is again 15 meters. So, this is also taken from the same source, that is Keyes and McCrary, 1971. So, the only difference between this and the short normal electrode arrangement is the distance is between the grounded current electrode, which is below the reference point, and the ungrounded potential electrode, which is above the reference point at the same distance. So, this distance is much higher, it is of the order of say 1.6 meters, while in the previous case it was just 0.4 meters. And now, let us come to the lateral arrangement. So, this is the long normal electrode arrangement, and now let us consider the lateral electrode arrangement. Again, this is from the same source, that is Keyes and McCrary, and in this lateral arrangement. So, the distance AO. So, this is the uncased well, and so here this is the reference point, and that is denoted by the letter O, and the electrode, the potential electrode M and N are on either side of this reference point, and there is a voltmeter, and so this is M. I am sorry, this is M is above this one and N is below the reference point, and the distance is much less, and in this case the current electrode A. So, this is below